Okay, so we're going to go through as many of these review slides as we can. Talk about some of the things that you need to know for your exam. Some of them are a little more straightforward. Some of them are going to involve a little bit of work. For this first one, what is the chemical symbol for bromine? This is one of the ones that you're going to need to know from your periodic table. There are certain elements that you get used to using over and over again, and those are going to be the ones that you'll be expected to like know from memory for your exam. So something like bromine, this is in the seventh column of your main group elements. And its symbol is going to be Br. Sometimes, when you get to slides like this too, like maybe you can test yourself on the other ones as well, because if you know what the other symbols mean, you can also like process of elimination that can help you figure out what the correct answer is. Next question, what element has a symbol AU? AU is one of the elements are a little on the weird side in terms of their symbol because it doesn't quite match up to its English name, right? So AU, that's going to stand for aurum, AUR, aurum, and that is our symbol for gold. The chemical symbol for potassium, super common element, have to know the symbol for this one. Potassium's name on the periodic table, excuse me, again, doesn't come from its English name. It comes from the name Kalium with a K, which is why its symbol is the capital letter K. The capital letter P, that's going to stand for phosphorus. So you don't want to get those two things confused. Next question, which of the following is an alkaline earth metal? So this is the first question that's going to really test whether you understand what the names of the groups on your periodic table are. So if we go back to making a bad sketch here, there's only certain columns on the periodic table that have specific names given to them. The first two columns do fall into that category. And then we have our middle transition. And then we have our last 6. Okay, so out of the categories on your periodic table, you need to know the name for group 1A, group 2A, group 7A, and group 8A. All right, those are names that you're going to be expected to know. Group 1A will be your alkali metals. Group 2A will be your alkaline earth metals. Group 7A would be your halogens. And then group 8A will be your noble gases. Okay, so now within this question, they give you the list of element names, and now you'd have to find them on the periodic table and see which of the things listed falls into your second column, your alkaline earth metal column. So sodium is going to be in our first column, it's an alkali metal. Magnesium is going to be in our second column. Aluminum is going to be in our third column. And silicon is going to be over in our fourth column. Excuse me. Okay. And Notice I'm referring to the columns as 1, 2, 3, 4. I'm skipping right over this rectangle. When you're counting your columns and you're looking at the column numbers, that's going to be true for your main group elements. Okay, so like when we talk about the valence electrons or elements, when we talk about columns that have similar properties, this is going to be largely true in our main groups. Things get a little bit less regular in our transition group, all right? So all of these are main group. And then all of these are main group. All right. So the answer to question number 4 is going to be magnesium. That is our alkaline earth metal. Okay, question number 5. We'll leave this ridiculous looking periodic table mock-up for now. To look at question number 5, let me just share it real quick. Which says, which element should have properties similar to those of sulfur? So here they're asking you to remember where the similarities on the periodic table are going to occur. Are they going to occur with atoms that are in the, or elements that are in the same row, or are they going to occur with elements that are in the same column? Okay. And just like the way that we've grouped these elements and we've said like everything in column 1 is an alkali metal, everything in column 2 is an alkaline earth metal. That's because everything in these columns are similar to each other. All right, like everything in column 8A, noble gases, these are all similar to each other. So when they ask you a question like this one, they want you to find sulfur on the periodic table. And they're going to want you to see what other elements are in the same column as sulfur, because those elements are going to have properties that are similar to sulfur. Okay, so sulfur and oxygen are going to have properties that are really similar to each other. Sulfur over here and sodium over here, those aren't going to be similar. Sulfur over here and carbon over here in column 4, not similar. Sulfur over here and argon over here, they're in the same row, but they're not going to be chemically similar. Sulfur has 6 valence electrons, so it's going to react like other things that have 6 valence electrons, other things like oxygen, like selenium. Okay. Our next question asks us which element is classified as a metalloid. And when you're looking on your periodic table at the metalloids, you have to be able to essentially draw that metalloid staircase for yourself on like a periodic table that does not have the staircase written. Okay. So if we start over at boron and aluminum, again, we'll do like a little sketch here. Boron, aluminum, gallium, silicon, germanium, arsenic, antimony, tellurium, polonium. Okay, so your metalloids are going to start up here with boron. Okay, Let's see if my green marker works a little better. Start here with boron. And then you're going to draw your staircase. Okay, so your staircase is gonna it's gonna include silicon. Okay, so it's gonna go from boron's included and silicon's included. And then your staircase is gonna branch out and include arsenic. And it's gonna include tellurium. And for this textbook, it's gonna include astatine too. Okay, and so now you're gonna come back here and you're gonna include your astatine and polonium. And then you're finishing off your staircase now. You're including your antimony, including your germanium. So now everything here that's shaded in green, all of these things, these are all your metalloids. Okay, everything that's not on that staircase is not a metalloid. So they give you, as choices here, they give you zinc. Zinc's over here on the periodic table, not a metalloid. They give you nitrogen, which is up here, not a metalloid. They give you iodine, which is down here on your periodic table, not a metalloid. And then they give you arsenic, which is right here. And arsenic is going to be your metalloid. Okay. That's question number 6. Next question asks, which of the following is a transition element? I'm just gonna check back in and share the screen, just so we have like a visual cue for what we're up to here. Which of the following is a transition element? So now we are going to, again, we're going to look at our periodic table. We recognize that this is our transition rectangle. And so we want to know which of the elements listed is going to be in our transition section. Okay, so I'm going to erase some of this stuff so we can look back at these options and see where they're at on the periodic table. All right, so the options that they give us are potassium to start with. So potassium is going to be in our first column. So it's in group 1A. We'll just approximate it down here. They give us bromine, which is all the way over in group 7. Neither of those are transitions. They give us chromium, which is Cr, which you'll find right here, and chromium is going to be our correct answer. And they also give us radon, which is somewhere down here on the periodic table. Again, it's a noble gas. It's outside of the transition box. Clearly, it's not the right choice. So choice C here, chromium, is going to be our correct answer choice there. All right. Next question. Sorry, I had to pause that a little bit. Asks us the number of neutrons that are in the nucleus of a bromine atom that has a mass number of 80. All right, and we're looking for the number of neutrons. And so the first thing that we're going to do is we're going to remember what mass number means. So when we're trying to find the mass number, that means that we're going to be adding together the protons plus the neutrons. This question's asking us to find the number of neutrons, okay? So let's look at the other parts of that equation. The mass number is something that they gave us in the question. They're telling us that the mass number for this atom is 80. And we can figure out the number of protons by looking at the atomic number of bromine. Okay, so bromine on the periodic table is atomic number 35, which means it has 35 protons. Okay, so to find my number of neutrons, I'm going to take my mass number of 80, and I'm going to subtract my 35 protons. Okay, and that's going to leave me with 45 neutrons. All right, and that's going to be answer choice C on our review. All right, next question. The number of electrons in an aluminum atom that has a mass number of 27 is. So this question gives you probably more information than you need to actually answer it. You have an aluminum atom. I'm going to write down the information first with a mass number of 27. Okay, and they're asking us here to find the number of electrons. Okay, and what we know about neutral atoms, and in this case, they're not telling us that we're working with an ion, they're telling us that we have an aluminum atom, which means that it's going to be uncharged, it's going to be neutral. If it was an ion, they would have said an aluminum ion, right? But if they say an aluminum atom, that means that we can think of it as something that's neutral. And if it's neutral, that means that whatever the number of protons is going to be, that has to be equal to the number of electrons we have. Okay, and to figure out the number of protons that we have, we're just going to focus in on where aluminum is on the periodic table. Aluminum is atomic number 13, which means it has 13 protons. And if we have 13 protons, that means that we're going to have 13 electrons in this atom. Okay, which is choice B. All right, let's look at the next question. This is a question about isotope abundance, but it's a little more conceptual than the math-based isotope abundance questions, which we can look at an example of shortly. But in this question, they're telling you that sulfur has 4 isotopes. And they're giving us the isotope symbol of each one. And remember that exponent, that superscript, that's in the top left corner, that's telling us the mass number of that specific isotope. Okay, and they say to use the atomic mass that's listed on the periodic table to figure out which of these isotopes would be the most abundant. All right. When you look at the mass of sulfur on the periodic table, that atomic mass is 32.06. Okay, and that's going to be from the periodic table. And what this question is asking you to understand is that the atomic mass that we calculate that shows up on the periodic table is an average mass value of all of these isotope masses multiplied by their isotope abundance, how abundant they are in nature. So when we look at the atomic mass of sulfur and we see that it's 32.06, what that should translate to in our heads is that it means that the isotope of sulfur that has a mass number of 32 is going to be the isotope of sulfur that's present most often in nature. Okay, so whichever isotope has a mass number that's closest to your periodic table atomic mass is the isotope that's going to be the most abundant in your samples. Okay. So in this case for us, it's sulfur 32, which is going to be choice A. It's question 10. All right. Next question. It says, how many orbitals are there in the 3D sublevel? Okay, so how many orbitals are there in the 3D sublevel? This question, I don't know, maybe it can be considered a little bit tricky, but this question, for this question, you should focus more on the type of sublevel that you're looking at, rather than the energy level that your sublevel exists in. So when you have a D sublevel, you can have a D sublevel that's in the 3rd energy level, the 4th energy level, the 5th energy level. But in every D sublevel, there's a maximum number of orbitals that can be in that sublevel, that can exist in a D sublevel. Okay. So remember that we have 4 different types of sublevels that we focused on. We had an S sublevel. We have a P sublevel. We have a D sublevel. And we have an F sublevel. Okay. And in our S sublevel, it can hold a maximum of 2 electrons. And because it can only hold 2 electrons maximum, and there are 2 electrons that fit into every 1 orbital, that means your S sublevels have only 1 orbital. Every S sublevel, whether it's a 1s, 2s, 3s, 4s, all of your S sublevels only have 1 orbital. Okay. For your P sublevels, they can hold a maximum of 6 electrons total. Okay, and again, you can have a maximum of 2 electrons that fit into every orbital. So all of your P sublevels are going to have 3 orbitals. Right? And each of these orbitals can hold 2 electrons. 2 times 3, 6 electrons total. And it doesn't matter which energy level your P sublevel is in, 2p, 3p, 4p. If it's a P sublevel, it has 3 orbitals. That's it. Okay. For our D sublevel, we're going to increase the number of electrons that we're going to be able to hold by 4. So we're always increasing by 4 electrons as we go into our next sublevels. So here we're going to hold a maximum of 10 electrons. And if we have 10 electrons, we're going to need 5 orbitals. Every d orbital has 5 orbitals. For our F sublevel, these are going to hold a maximum of 14 electrons. And if we have 14 electrons, that means our F sublevel will have 7 orbitals. Every F sublevel has 7 orbitals. So in this case, we have a 3D sublevel. It's going to have 5 orbitals in it. All right. The next question says, share so we can look at it. What is the maximum number of electrons that are possible in the energy level 4? All right. And so now for this one, we have to think about all of the different sublevels that can exist in our 4th energy level. Okay. I would say that for a question like this, it'd be a good idea in your scrap paper to maybe sketch out for yourself a little diagram of our nucleus and then the energy levels that kind of exist outside of that nucleus, you know, going from about 1 to 4 or so. Kind of like what we did on the board when we were talking about this initially. So like you have your nucleus, then there's some empty space. And then we're going to have our first energy level, okay? So this is going to be n equals 1. And in your first energy level, the only sublevel that exists is going to be your 1s sublevel, right? And after your first energy level is your second energy level. So now within this space, we're going to have n equals 2. And within your second energy level, you can have a 2s sublevel, and you can also have a 2p sublevel, right? And you want to do that for the first energy level, the second, the third, and the fourth. For every additional energy level, we're going to add a new sublevel to it. So when our n value is 3, we're going to be able to have a 3s sublevel, a 3p sublevel, and a 3d sublevel. All right. And the highest that we're going to go is to our 4th energy level. And for our 4th energy level, we're going to have a 4s, a 4p, a 4d, and a 4f. Okay. Now figuring out how many electrons are possible, we can kind of go back to that picture we just had for the last question, right? If we have a 4s orbital, we know that that can hold a maximum of 2 electrons. If we have a 4p orbital, our p sublevels rather, can hold a maximum of 6 electrons. When we're looking at the 4d sublevel, every d sublevel can hold a maximum of 10 electrons. And for our 4f sublevel, F sublevels can hold a maximum of 14 electrons. So if I want to know the total number of electrons that could be in the 4th energy level at the same time, I can just look at all of these electron values from my different 4th energy level sublevels, and I can add them together. right? 12, 32. 32 electrons total, which is the answer to this question. If they had asked me what's the maximum number of orbitals that existed in the fourth energy level? If I know I can have 32 electrons maximum, that means that I would need 16 orbitals to hold them. Okay. So that was answer choice B there. All right. Next question asks us to find the electron configuration for calcium. All right, so we find calcium on the periodic table. It is going to be in the fourth row. It's gonna be in the fourth row. And it's gonna be the second element over. It's number 20 on the periodic table. So we know that it's gonna have 20 protons. And if it's neutral, it's gonna have 20 electrons, right? And it's telling us here that if it's not telling us that we're looking at the ion, we can assume that it's neutral. And so we wanna fill these 20 electrons in the order that our periodic table tells us. So we start with our 1s sublevel, we fill that first, and our s sublevel can have 2 electrons in it. Then we're gonna move on to the second energy level. And in our second energy level, we have a 2s sublevel and a 2p sublevel. Our s sublevel has 2 electrons, our p sublevel has 6 electrons. So far we've used 6, 7, 8, 9, 10 of these electrons up. So we still have to put 10 more electrons into our configuration. So we go into our third row. And we're gonna fill our 3s sublevel. And then we're gonna move over to our 3p sublevel. That's also full. We know that it's full because we haven't reached 20 electrons yet. Like right now, this was 10, 11, 12. 12 plus 6 means I've used 18 electrons total, and I still have to put 2 more in. And after we fill the 3p sublevel, the next sublevel that we're going to fill is going to be the 4s. Okay. Remember that we have to fill the 4s before we can fill the 3d. Okay, and in the 4s sublevel, that's where the last 2 electrons are going to go. Okay, and if we add up all of our electrons, all of the superscripts up top, we'll see that they add up to 20. That's our configuration, and that was going to be choice A from the answers that were given there. All right, the next question, number 14, asks us to find the element that has the electron configuration that they're giving us. Okay, so they bracketed off neon, and then they gave us 3s2, 3p1. So on your periodic table, when you're looking at something like this, you're going to find neon. Again, we'll just use this terrible version of the periodic table. So neon's going to be over here. Okay. That means, so what they're saying is that the element that you're looking for has the same electron configuration as neon. But then in addition to that, it's got these extra 3 electrons. Okay, so you're going to go to neon on your periodic table and you're going to say, all right, well, I'm looking for something that has 3 more electrons than this neon. And so you go down to 3s, right? And now you're looking at sodium and magnesium. Up to there is 3s2. Then we skip over our little transition metal group. And now right over here is aluminum. Aluminum, which has 13 protons and 13 electrons, right? So it's going to have 3 more electrons than neon would. So this is going to be the electron configuration for aluminum. Another way that you can figure this question out is that you can look at the last addition to your electron configuration, your 3p1 in this case. And if you remember how we talked about reading the periodic table, let me share my screen to this periodic table here. So remember we said that everything in these first 2 columns is going to be considered in the S block, okay? And except pretend that helium is back over here by hydrogen. So if you focus on that 3p1, you can find where 3p1 is on your periodic table. You know that the 3 tells you that it's going to be in this 3rd row, okay? This is your S block, so it's not here. This is 3s1 for sodium, 3s2 for magnesium. And now if we travel over here to our P block, the first element in our P block in the 3rd row is aluminum. So aluminum is going to have its final electron in the configuration be 3p1. Okay. Silicon's final electron, 3p2. Phosphorus's final electron, 3p3. Okay, so you can use the position on the periodic table to help you answer a question like that as well. All right. Next question says, what is the correct Lewis symbol for lithium? Lewis symbols were kind of like what we were drawing for when we were making our Lewis structures. To figure out the Lewis symbol for an element, you're going to find the element on the periodic table. So lithium is in group 1A. And that means it has 1 valence electron. And to write its Lewis symbol, you're going to write the letter symbol down for your element. And then you're going to position however many valence electrons it has, you're going to position those electrons around it. Lithium only has 1 valence electron, so we're just going to put 1 electron outside of that lithium symbol. Okay, and that's going to represent your Lewis symbol for lithium. All right. Next question says, which of the following elements has the smallest atomic radius? Okay, so for this question, we kind of want to remember the trends for size on our periodic table. So think about the periodic table, try to be able to recreate these trends for yourself in your note paper. Remember that your smallest element is going to be, they're going to be to the top right, and your largest elements are going to be down here. Okay. So as we go from left to right, we're going to be getting smaller. And as we go from the bottom to the top, we'll be getting smaller as well. If you have something like this sketched out, the reason I think it's going to be helpful is because then you can place the answer choices on your mocked up periodic table, and you can like then do a direct comparison. Okay. Lithium, boron, carbon, and oxygen are all in the same row of the periodic table. Lithium's over here, boron's over here, carbon's next to it, and then oxygen's a little further over. But when you list them out like this on the periodic table, instead of just one after the other on, like on the answer sheet has, that now you've listed them in a way where you can directly compare them to your trend. So we see that, well, if our sizes get smaller as we go to the right, then out of all of these choices listed, oxygen has to be the smallest one. Okay. So there's going to be ways for you to set up these questions for yourself on your scrap paper. That's going to make it a lot easier to get to the right answer. The following question, number 17, says, which of the following elements has the largest atomic radius? So it's just a spin off of the same type of question, but the elements that they're going to give us to look at different. So here they're telling us carbon, silicon, germanium, and tin, all right, which are all in the same column. So carbon's up top, then silicon, then germanium, then tin. And we see from our trend here, whatever's up top is going to be smallest, whatever's on the bottom of this column is going to be largest. So the thing with the largest atomic radius is going to be tin in this case. Which is symbol SN. All right, the next question asks us to arrange the elements K, CS, and SE in order of increasing atomic radius. Okay. So again, I would stick to my little rectangle that's representing my periodic table here. And first, I'm going to just place these elements in my periodic table, like kind of approximately where they are in reality. So like potassium is kind of in the middle of the periodic table, but it's all the way on the left. And selenium is in the same row as potassium, but it's closer to the right side. And then cesium is in the same column as potassium, but it's lower. Okay. Now, if they want me to list this in increasing order of radius, that means they want me to start with the smallest and they want me to end with the largest. Okay. So out of all of these things, my smallest thing is going to be whatever is furthest up top and furthest to the right. So out of all of these things, selenium is going to be the smallest. Okay. After selenium, now that I've picked out my smallest one, I'm going to compare potassium and cesium. They're in the same column. So I'm going to look to see whichever one is further towards the top, because that's going to be the smaller one. Okay. And then my largest one is going to be my cesium. So my selenium is going to have less of a radius than potassium. Potassium is going to have less of a radius than cesium. All right, and that's how we're going to get that ordering. And that is going to be answer choice D. All right, the next question asks us to arrange strontium. Just write the question number. They're asking us to arrange strontium, magnesium, and chlorine in order of increasing ionization energy. All right, and just like we did with the size stuff, we're going to make a little, some trend lines to represent ionization energy. Remember that when we say ionization energy, we're talking about the energy that's needed to remove an electron. All right. And in general, metals have really small ionization energies. IEs. And our non-metals are going to have larger IEs, larger ionization energies. Okay. So when we're looking across a row on our periodic table, we're going to have small to large for ionization energies. And then in terms of top to bottom of the periodic table, our ionization energies are going to get smaller the further down they are. Okay. So when we're looking up and down on the periodic table, we're going to have smaller ionization energies on the bottom and larger ionization energies up top. Okay. So let's use those trends to put these particular atoms in ionization energy order. We're going to be we're trying to arrange them in increasing order. So again, we want to list them from smallest ionization energy to largest. Okay. And they're giving us strontium and magnesium. So magnesium is in our second column, and strontium is 2 elements below it in the same column. And then chlorine is in the same row as magnesium, but it's further to the right. Okay. So first, if we're looking, we can look between our left side and our right side first. Chlorine versus magnesium and strontium, that's going to have the largest ionization energy. It's furthest to the right, and it's as far up as magnesium is. So our largest ionization energy is going to be chlorine. Out of magnesium and strontium, magnesium is further up on the periodic table, so it's going to have a bigger ionization energy. Strontium is further towards the bottom, so it's going to have a smaller ionization energy. So strontium will have our smallest, magnesium will be in the middle, and then chlorine will have the largest. So strontium is less than magnesium, magnesium is less than chlorine. Okay, and that's going to be answer choice B. And the final trend question is a trend that's asking us to arrange 3 elements in order of increasing metallic character. Remember that metallic character is going to be related to ionization energy. because it's like an exact inverse relationship or, indirect relationship. Things that have very low ionization energies have very high metallic character. Okay. So in terms of metallic character, we're going to see that our most metallic element is going to be down here. And this is where our lowest ionization energy was. And our least metallic will be up here. And this is where our highest ionization energy was. Okay. So we're going to get more metallic as we move from right to left. And we're going to get more metallic as we move further down. All right, so the elements that they've given us to do this comparison of right now are going to be carbon, lead, and carbon, germanium, and lead. So let's find those all in the periodic table. So carbon is up at the top of column 4. And then they give us germanium, which is a couple of elements down. And then they give us lead, which is a couple of elements below that. So these are all in the same column. So they're really just asking us to compare vertically. Like in this column, what's going to be the most metallic and the least metallic. And we know that within any column, whatever's furthest to the bottom is going to be the most metallic thing. So if we're listing these in order of increasing metallic character, that means that we're going from least metallic to most metallic. Okay, and our least metallic here is going to be our carbon, and our most metallic is going to be our lead. So carbon is going to be less metallic than germanium, and germanium is going to be less metallic than lead. All right. So those were the review questions from chapter 4. The next set's going to go into chapter 5, which we talked about nuclear chemistry. So some of these questions, at least at the beginning, we can kind of talk through. Share my screen. This first question says an alpha particle is the same as what? Okay. And they give us these options here. Helium-5 nucleus, helium-4 nucleus, helium-3 nucleus, and a proton. All right, let's sketch out what each of these are. So let's look at each of what these things mean, because I think that if we understand what the words are saying here, then it makes the answer a little bit easier. When they say a helium-5 nucleus, they're talking about something that's helium, and it's going to have 2 protons and a mass number of 5. That does not look like the alpha particle we've discussed before. Helium-4 nucleus, helium, 2 protons, mass number of 4. That looks exactly like the alpha particle we've been talking about in class. Helium-3, protons 2, mass number 1, so not these. And then a proton is going to have it's going to be like 1 proton, mass number of 1, and it'll have a little p. So that's the symbol for a proton. That's not the symbol for an alpha particle. Okay, so choice B was our answer there. That was for question 21. The next question says, which particle is the same as a high energy electron? Well, we know it's not alpha particles because we just wrote out what an alpha particle is. That's not an electron. Our positrons are exact opposites of electrons. Gamma rays are going to just be high energy radiation. And the only thing there that is going to be the same thing as a high energy electron is going to be a beta particle. And the symbol for our beta particles are going to be a zero on the top, a -1 on the bottom, and then a little lowercase e. You can also see beta particles written as a script EB and like a negative sign sometimes. The next question says, which of the following is the most penetrating? So remember that in terms of penetration and damage, there's like an inverse relationship there. So your smallest radiation is going to be the most penetrating radiation. And out of all of those particles listed, your gamma rays are going to be the smallest. Okay, that's your most penetrating radiation. All right, next question gives us a nuclear equation, and they ask us to find, just to identify it actually. They're giving us this nuclear reaction. So we start with boron 8, and then it's going to convert into beryllium 8, and it's going to release this particle. And knowing the identity of that particle answers this question, because remember that the type of nuclear decay, the class of nuclear decay is going to be based on the radioactive particles that are involved in the process. So here, this is a positron. And so this type of decay is called positron emission. Okay. Okay, the next question does ask us to find the product of a decay. So we're gonna sketch this out. Tells us that uranium-238 is gonna decay by an emission of an alpha particle. And then it asks us what the product is. So when you see a question like this, decays by emission of an alpha particle. that means that you know that this alpha particle is going to be on your product side of your nuclear reaction. Okay, so you're starting out with uranium-238. That's your parent nuclide. And then on your product side, you're going to release an alpha particle. And now we're going to figure out what the other product is. And this other product, this is going to be the thing that we're going to match to one of the answer choices. Okay, and so remember, everything on the top and the bottom here has to even out. So they've given us this symbol, U238. So now we can rewrite this so it looks more like this format. That 238, that's going to go up here. That's the mass number. And to figure out the bottom number, we're just going to find uranium on the periodic table. It's number 92. And that atomic number 92 is what goes on the bottom there. Okay. And now with that information formatted this way, it's going to be much easier to find this missing particle. We know that we have a 92 on the bottom, and over here we have a 2. So our missing atomic number must be 90. We have 238 up here, and we have 4 over here. So 234 must be our missing mass number. And then we'll find number 90 on the periodic table. Number 90 is thorium. And that's going to be our missing symbol, our missing product. So that is going to be answer choice B. All right. The next question asks us, it's another type of decay question, but the way that they're asking it's just a little bit different. Here they're saying, they're telling you that you're starting with radon-222. Okay. It says that you have this isotope and it's going to decay and it's going to form this isotope. And it says through what process. Okay. The way that you're going to figure out what process it is you're going to figure out what the missing particle is. What's the missing piece of this equation? And how do you figure out the missing piece? Well, you say, I've got 86 over here. I have 84 over here. So this particle has a 2 on the bottom. I've got 222 here. I've got 218 here. I'm missing a 4 up top. And if I have a 2 on the bottom, that's helium. So this is an alpha particle. That means that the type of process that happened is going to be alpha decay. All right, so you find the particle and then you link the particle to the decay type. All right, we have another question similar to this for number 27. They're telling us that this iron isotope, iron 56, is going to decay to manganese 56 through what process? So that means that we have to find our missing particle. Okay. We see that up top here, 56, 56 needs to be a 0 up top. We have a 26 here, and then we have a 25 here. So we're going to need a +1 on the bottom down here. And the only type of radioactive particle that has a 0 and a +1 is going to be your positron. Okay. So if that's a positron, that means that this process is going to be called positron emission. All right, the next question is just the definition. It says the unit that's used to describe the actual amount of damage done to tissue by a given amount of radiation is, and the answer to that is going to be the REM unit. So that one is just going to be one of the definitions that you should be familiar with. The question after that says, which of the following forms of ionizing radiation has the most mass? Hopefully this is one that you remember us talking about a couple of different times. Our alpha particles are going to be the most massive radioactive particle that we have available, or that we know about. They're the size of a helium nucleus. That means that they're going to have 2 protons and they're going to have 2 neutrons. Okay, so they're big. Beta particles are essentially the size of an electron, which are tiny. Neutrons, this has got 2 neutrons and 2 protons in it, so a single neutron is definitely going to be smaller. Positrons are going to be the same size as beta particles, just oppositely charged. So the biggest thing on this list is going to be that alpha particle. And question number 30, this is a good thinking question too. It says, loss of the following does not result in a change to the atomic number. Okay, and for each of these, you have to ask yourself, like, look at the symbol that you can write for each one of these, right? Each one of them has a symbol that represents them. And in that symbol, you have the superscript and the subscript exponents. That subscript exponent, that's going to represent your number of protons, your atomic number. So any of these particles that have a value in that subscript part, those are things that will change your atomic number. Alpha particles, right? They're going to change your atomic number by 2. So that can't be the right thing. Beta particles, there's a 0 up top, but that's the mass number. There's a -1 down here. So when you have beta particles, beta decay, you're going to be increasing your atomic number by 1. So that's a change. So that doesn't answer that question. When you have positrons, which are kind of related to your beta particles because they're opposites, right? There's a +1 down here. That means that when you have positron emission, your nucleus is going to be losing one of its protons. Its atomic number is going to decrease by 1. So positrons aren't going to be the answer to this question. But if you write out the symbol for a neutron, the neutron symbol is a 0 on the bottom because a neutron doesn't have any protons. It's a 1 up top because it's just the neutron, and then the little n. So when you're working with your neutrons, when you remove a neutron, the atomic number is not the thing that changes. Okay, there's no change in your atomic number here. All right. That's a good first start. That's the first about half of these review slides, and we'll see if we can come back in and talk through the rest of them in a little bit. All right, so let's tackle this next set of questions. With the next question, we have a half-life question. It says that the half-life of a radioactive element is 8 years. What percentage of the original sample would be left after 64 years? So we're going to note our half-life. And we're going to note how much time has passed. It's, write that a little cleaner, 64 years. Okay. And the, stop sharing, there we go. And so the first thing that we want to figure out is how many half-lives have gone by. Okay, so every 8 years is going to be a half-life. So when we start at time 0, which is the beginning, and we go up to 8 years, this is going to be our first half-life. And now another 8 years is going to go by. So we'll say plus 8 years. Now we're at 16 years. That's our second half-life. 8 more years is going to go by. We're up to 24 years. That's our third half-life. Okay, see our trend here, plus 8 more years. Now we're up to 32 years. All right, we're gonna just keep going on this next line. So we're gonna add 8 more years to that. And now we're up to 40 years. That's our fifth half-life. I know this seems tedious, but especially if you're struggling a little bit with half-life, this is the easiest way to visualize it for yourself. Okay, so plus 8 more years, we're gonna be up to 48. That's our sixth half-life. Plus 8 more years. Now we're up to 56 years. That's our seventh half-life. Okay, and then we add 8 more years to that. And now we're going to be up to 64 years. Okay, that's our eighth half-life. So 8 half-lives have gone by. That means that the material that we start with is going to be divided in half 8 times. Okay, so now if we take our same like map that we've just made here, we're going to remember that at time 0, at the beginning, we're going to have 100% of our material. And at our first half-life, we're going to lose half of that. So now we're going to have 50% of our material. At our second half-life, we're going to lose half of that. So now we're going to have 25% of our original material. So every half-life that passes, we're going to be dividing what's left by 2. So half of 25, 12.5%. I'm going to start needing my calculator to divide some of these by 2 because they're going to get small. When we take our 12.5 and we divide it by 2 for our fourth half-life, we're going to have 6.25%. Then we're going to divide our 6.25% by 2 for our fifth half-life. And we end up with 3.125%. All right. Then for our sixth half-life, we're going to divide what's left by 2 again. And we end up with 1.56% for our sixth half-life. And we take our 1.56 and we divide it by 2 again for our 7th half-life. Okay. And then for our 8th half-life, we're going to divide it into one more time. Okay. Sorry, I should have been 0.78. All right, so after the 8th half-life goes by, this is how much of our original sample that we would have left. You start out with 100%, and at every half-life, we're going to lose 50% of whatever we have left. Okay, so by our 8th half-life, we end up with 0.39% of our original material. All right, next question. Another half-life question. This one says the half-life for the radioactive decay of calcium-47 is 4.5 days, 4.5 days. How many half-lives have elapsed after 18 days? Okay, so there are a few ways that you can look at this. There are a few ways you can solve this problem. One way that they talked about in your textbook was you can make yourself a little equation that's basically the number of half-lives is going to equal the total amount of time that's passed divided by the length of your half-life. So if you know that 18 days has passed and your half-life is 4.5 days, you can say, all right, well, 18 divided by 4.5 is going to be 4. So 4 half-lives have gone by. All right, that's one way you can look at this. The other way, and especially if, again, if you're having trouble visualizing it, that's not a big deal because you could still handle this. You're just going to count by 4.5 days. So you're just going to say from 0 days, which is our starting point, to 4.5. That's going to be 1 half-life. From 4.5 days, I'm going to add another 4.5 days, and I'm going to get 9 days. That's my second half-life. I'm going to add another 4.5 days to that. 10, 11, 12, 13.5. That's my third half-life. And then I'm going to add 4.5 more days to that. And that's going to give me my 18 days. And at 18 days, that's my fourth half-life. So either of those methods would be fine for figuring out the number of half-lives that have gone by in a certain time period. All right, next question. It says iron 59 has a half-life of 46 days. If the laboratory received an 8-gram sample of iron 59, the number of grams that are still active after 184 days is blank. So we want to know how much is left after 184 days. Okay, and again, this kind of goes back to that first thing that we talked about. Your first step here, step 1, find how many half-lives have passed. And then once you know how many half-lives have passed, you can track the decay of your original amount. Okay? So if we're starting at time 0, when we reach 46 days, that's 1 half-life. All right? For our second half-life, we're going to wait another 46 days. And then we're going to be at 92 days. That's our second half-life. Then we're going to wait 46 more days. And we're going to get to our third half-life. So that's going to be at 138 days. Okay. And then we're going to wait 46 more days. And now we're at 184 days. So at the 184 day point, that's going to be our fourth half-life. Okay. And so now, again, we go back to our original starting amount. We started on day 0, we had 8 grams. All right. And after our first half-life happens, we're only going to have 50% of that left. We're going to have half of it left. So at our first half-life, we're going to have 4 grams left. After 46 more days goes by and we reach our second half-life, we're only going to have half of this left, half of our 4 grams left. Another 46 days goes by and we're going to lose half of this. So now we're going to have 1 gram left. Another 46 days goes by, and at our next half-life, we're going to have half of this left. Okay. So this is the amount that we're going to be left with after those 4 half-lives have gone by. But our steps are, first, find how many half-lives have passed, and then use that to help you figure out how much is left after that number of half-lives have gone by. All right, I'm going to share my screen for the next question because I want you to see some of this wording. Again, it's another half-life question, but we want to look at how this is worded. It says, suppose that a piece of wood found in a tomb has 1/8 of its original C14 activity. Remember that C14 activity, it is related to how alive something was, okay? You'd imagine that C14 in something that's living is the activity is going to be 100%. All right, so after 3 half-lives, that means it's gone from 100% down to 50%, 50% down to 25%, and then 25% down to 12.5%. Okay, so 3 half-lives means you're down to 1/8 of its original activity, or 12.5%. Okay, they're telling you that 3 half-lives have gone by. They didn't have to tell you that. They could have just said that the tomb has 1/8 of its original carbon-14 activity and kind of asked you to figure out how many half-lives is going to be equivalent to 1/8 of that original activity. So remember that if we're not talking percentage, if we're talking in fractions, we're starting out with a whole number, whole 1. And as we move through our half-lives, this whole number is going to turn into fractions. So half of 1, at our first half-life, we're going to have 1/2 of our material left. At our second half-life, we're going to have half of 1/2, which is 1/4. And at our third half-life, we're going to have half of 1/4, which is going to be 1/8. Okay, so when they told us that we had 1/8 of our original left, that was their way of telling us that 3 half-lives have gone by. That's our first, that's our second, and that's our third. Now, the information that they didn't tell you in the question that would be provided if this was an exam question is the actual half-life of carbon-14. That's not something that you have to memorize. It's something that will tell you. So carbon-14 has a half-life of around 5,730 years. Okay. So now, if we know that 3 half-lives have gone by, we know we can figure out how old this piece of wood that's in the tomb would be. Because after our first half-life goes by, we know that 5,730 years has passed, right? This was the 0 marker. And our first half-life is going to be 5,730 years. When we reach our second half-life, we're going to be adding another 5,730 years to our first amount. Need a calculator for this for sure. So at our second half-life, that means that 11,460 years has passed. And then to reach our third half-life, we're going to be waiting another 5,730 years. And we're going to be up to 17,190 years total. So this would be the age of that piece of wood after 3 half-lives have gone by. All right. The next question is more of a concept question. It says, which of the following is true for radioisotopes that are used in medicine? Share the screen so we could look at some of these choices. So we're looking at stuff that's going to be good for medicine. So remember that what we talked about in terms of radioisotopes and what types of radioisotopes that we're going to want to use in what kind of radioisotopes we're going to want to use like in our bodies. We're going to want any radioisotopes that have short half-lives, that are not going to linger. Okay. This first statement, they only produce alpha particles. We definitely don't want alpha particles rolling around in our body. Alpha particles are big, they're going to cause a lot of damage. Half-lives measured in days, that days or hours are the best types of half-lives. We want half-lives, we want radioisotopes that have half-lives that are super short. Okay. We do not want to have to take large doses. We want to keep the doses small. And this last statement, the body rejects radioisotopes. We wouldn't want that to happen. Okay. The following question, which the following radioactive isotopes is useful in the investigation of thyroid problems? We can look at the answer to this one. This type of question, we're not going to be memorizing like specific isotopes and their specific body parts, but the iodine for that one would be the correct answer. Scanners using radioisotopes are capable of gathering information on. Okay, so if we're using radioisotopes, this is a question you should be able to answer. If you have ingested a specific type of radioisotope and then you are using a scanner, what are things that you can scan with radioisotopes sort of in the right spot? Like pretty much anywhere that they can travel in your body, right? So can they go into tumors? Sure. Can they go into your soft tissue? Sure. Can they move around in your blood? All of those things. Anywhere that a radioisotope can go in your body is a place where it can give you information. Okay. And depending on what it is you're looking specifically at, that's where your scanners are going to focus. Okay. But they could potentially gather information in all these things. In the equation, E equals mc squared. What does m represent? We didn't have a chance to talk about this in your textbook. They didn't put this into the notes, but we can talk about it. The energy equation is going to be the mass times the speed of light squared. Okay, the mass times the speed of light squared. And specifically, we're looking at the mass that's technically lost when your nucleus is undergoing changes. Okay. There's something that if you look more into your nuclear chemistry in like later chapters, there's something called nuclear binding energy. Energy that's going to keep your nucleus together. Part of this energy equation here is related to the nuclear binding energy of your atoms. Okay, so when you look at Einstein's equation, that m value there stands for that mass value that we're seeing lost. It's still there, but it's going to be represented in terms of the energy. Which product of the fission of uranium-235 causes a chain reaction to occur? Now, we sketched out the fission reactions a bit in class. And remember that there's one product that occurs from the fission that then allows the reaction to continue to progress and grow. Okay. And that specific product is going to be these neutrons that form. When your uranium-235 splits apart, it's going to split into the two smaller nuclei, and it's going to produce 3 neutrons. And each of those neutrons is going to go find another uranium-235 to split apart. Okay, so as long as you have an abundance of neutrons, your chain reaction is going to continue to progress. All right. Remember, that's why we talked about those control rods being a part of your nuclear reactor, because your control rods are able to absorb the neutrons and then potentially stop your fission reaction from happening. Last question is on fusion here. All of the following are characteristics of fusion except. When fusion, remember, that's when you're taking 2 smaller nuclei and you're joining them together. Okay, so large amounts of energy are released. Yes. Small nuclei combine to form larger nuclei. Yes. Very high temperatures are needed for the reaction. Absolutely. That's why fusion happens on the surface of the sun. Very, very hot. It is readily available as an energy source on Earth. This last statement is the untrue statement. The temperatures that fusion occurs at are so high that we actually can't harness it anywhere on Earth. All right, so I think, yep, those were our chapter 5 questions. So we're gonna work on some of the the chapter 6 questions next, and we'll see how far we get. All right, which of the following represents the number of protons and electrons in a bromide ion, Br minus? Okay, so scoot back over here to the board. Bromide ion, Br minus. Remember, that means that the bromine is going to have a -1 charge. All right, so you're going to look at your periodic table and you're going to find your bromine. Bromine starts out when it's neutral with 35 protons and 35 electrons. Okay, so when you're forming the bromide ion and it has a -1 charge, that means it's going to have one more electron. Okay, it's going to have one more electron than proton for it to have a -1 charge. Okay, when you're making ions, protons never change. Okay, only electrons change. Okay, so 35 protons rather, and 36 electrons. This would be the final count in our bromide ion. And that is, excuse me, that is choice C. All right. The next question says, what is the symbol for the ion formed by sulfur? All right, and so to answer this question, you're going to find sulfur on your periodic table. Sulfur is in group 6A, right? You have oxygen and then you have sulfur. And so you're going to say to yourself, sulfur is a nonmetal. If it's a nonmetal, it's going to gain electrons. And the number of electrons it's going to gain, you're going to look at your column number, 6. It's going to gain as many electrons as it needs to get to 8, a total of 8. So if it has 6 valence electrons, it's going to need to gain 2 more electrons. Okay, gains 2 electrons to reach 8. So our final symbol is going to be sulfur with that -2 charge. All right, next question. How many protons and electrons are in the Mg2+ ion? All right, protons never change. So you're going to go over to magnesium on your periodic table. You're going to find that. It's atomic number 12. So that means that it has 12 protons. That does not change. What's going to change is the number of electrons in relation to the number of protons that are present. So here, if we want to have a +2 charge, that means that we're going to want to have 2 more protons than electrons. Okay, so if I have 12 protons and I have a +2 charge, that means I can only have 10 electrons. Okay, And that's going to be answer choice D. All right, which FYI is not the answer choice that they have highlighted as the correct answer there, but that's a mistake on their part. Answer choice D is the correct one. All right, next question is asking us to write a formula for magnesium oxide. The first thing it's going to be helpful to do here is recognize that this is an ionic compound. Magnesium is a metal. Your oxygen is a nonmetal. So when these combine, they're going to combine based on charge neutrality. And that's an important first thing to recognize so that you know like how you're supposed to put the elements together. Okay. When you look at magnesium on the periodic table, it's in that second column. So it's going to have a +2 charge. Magnesium always has a +2 charge. Oxygen's in column 6A, meaning it wants to gain 2 electrons. So when oxygen gains 2 electrons, it's going to have a -2 charge. So those are the ions that are coming together to make magnesium oxide. And so now you want to ask yourself, well, when these two things join up, like how many oxygens do I need to balance out the charge on magnesium, or vice versa? And we see that these numbers, they're the same number, but they're opposite signs. And that means we only need one of each. If we have one magnesium, we only need one oxygen to neutralize that charge. So this is going to be our formula for our magnesium oxide. Okay. All right, let's look at our next one. It says the name of the compound whose formula is CaBr2. All right, this question is important to talk about because here's our choices here. Choice A, calcium bromide. Choice B, calcium dibromide. Choice C, calcium 1 bromide. Choice D, calcium 2 bromide. All right. Knowing the type of compound that you are working with limits what your answer could possibly be. Okay. You have to recognize, one, is your compound ionic or covalent, molecular? You have to answer that question first. Then the second question you have to ask yourself when you're naming your compounds, do you have a type 1 metal or a type 2 metal? Okay, our type 1 metal charge never changes. And for our type 2 metals, the charge can change. Every single time that you name a compound, you must answer these questions if you want to do it correctly. Okay. So you start with the first question here, ionic or molecular? Calcium is a metal. Bromine is a nonmetal. And that means that this compound is ionic. And with that first determination, you can already eliminate one of those answer choices. If it's an ionic compound, you absolutely, under no circumstances, can use any prefixes. You cannot use any prefixes. So now once you know it's ionic, you can look at this answer list and you can focus right here on this choice that has a prefix in it. And it doesn't matter what else it says, that prefix is there, that answer is wrong. Cannot have a prefix in it. Now you go to your next question. Is calcium a type 1 metal or a type 2 metal? Calcium is in column 2. Every single metal in column 1 and column 2 is a type 1 metal. Their charge never changes. Calcium's charge is always +2. And once you know that it's a type 1 metal, make a little arrow here. For any type 1 metal, you cannot use parentheses in your name. Okay? If you have a metal whose charge does not change, you cannot use parentheses to try to describe the charge or the number of calciums. This one would be wrong anyway because this one doesn't make any sense. But regardless, type 1 metals do not use parentheses. If you have a type 1 metal, the only thing that you're going to do to name your compound is write the name of the metal and follow it by the anion name, which is the beginning part of your nonmetal and an IDE ending. All right, next question. We worked a little bit on this in the compound lab with some of the charges, looking at how you figure out charges from compounds. But this question says, what's the charge on iron in Fe2O3? Iron is a type 2 metal. Iron's charge can change depending on what it's combining with. So if you want to find the charge on the iron in a specific compound, you have to look at the anion to help you figure out what the charge on your metal is. The charge on your anion is never going to change. Oxygen's charge is always -2. And here I've got 3 oxygens. So you can picture it. Each oxygen will be, let's write it out like this. We've got 3 oxygens, so we're going to have O2 minus, O2 minus, O2 minus. Okay? That means that our total negative charge is going to be -6. What this first part of my formula tells me is that I have 2 irons. So I know I'm going to have 2 of these. And so now you have to ask yourself, you only have 2 irons, and they're going to have to add up to +6 so that they counteract this -6. So then you ask yourself, well, then what's the charge on each one of these irons, right? So the charge on each iron is going to be +3, so that it can balance out 3 -2s from your oxygen. Okay, so for this one, it's going to be Fe 3+, which is choice D. So now our next question, number 47. They want the name of the compound whose formula is AuCl3. Again, they're giving us It's important to look at the choices here because you have to know how to eliminate the ones that do not make sense. Because a lot of these choices are going to sound really good. And so it's going to be up to you to like find the nonsense and get rid of it. Okay. We're going to go through the same set of steps we talked about before. First question you ask yourself, is this ionic or is it molecular? We know that gold is a metal. Chlorine is a nonmetal. So right away, we know that this is ionic, and ionic means no prefixes. And so we're going to go over to our list of answer choices, find the thing with the prefix in it, cross that out. No good. Second thing, we look at gold, and now we're like, is gold type 1 metal or a type 2 metal? Gold is in the transition box, and that is where we find the majority of our type 2 metals. And if it's a type 2 metal, that means that we must use parentheses to tell us the charge on gold. The parentheses does not tell us how many golds we have. That is not what it's for. The parentheses is there to tell us what the charge on gold is. And to figure out what the charge is, we have to go back to its formula. And we have to use our anion to figure out what our metal is. We have 3 chloride ions. Each chloride ion has a -1 charge. And that means that the total negative charge here is going to be -3. We only have 1 gold. And if that gold has to neutralize this -3, that means that gold has to be +3. This 3, that is what has to be represented in those parentheses. Okay, so we need to have parentheses, so that can't be the right choice. And what's inside of the parentheses has to represent our charge. So this one can't be correct. So choice D is our correct answer here. Gold 3 chloride. All right. Next question says, write the formula for a compound that contains ammonium ions and phosphate ions. All right, so for these, you need to look up the formulas for each type of ion. And then you're going to include the charge because we're going to have to combine them so that the charges balance out. If you look on your table, like use your reference sheet here, like get used to using that. The ammonium formula is NH4 and it has a +1 charge. Your phosphate formula is PO4, -3 charge. And when we look at the charges, these have to equal each other, right? They need to be equal and opposite. So if I have a +1 here and a -3 here, I'm going to need 2 more ammonium ions to end up with enough positive charge to cancel out this charge, this -3. And when I write out my formula, it has to reflect 3 ammoniums, 1 phosphate. Okay, so with my polyatomic ions, I'm going to keep them inside of the parentheses. if I need more than one of them. So I put my ammonium ion in parentheses and I put this 3 on the outside so that I know that I need 3 of these. And I just need the 1 phosphate, so I'm going to follow this up with PO4. All right, and that's going to be my formula. Looks like choice D. All right. For question number 49, they're asking us to name Ca3, PO4, 2. Okay, and again, this naming process, this doesn't deviate. We have a metal here. We have a polyatomic ion here. We know that this is an ionic compound. Okay. We are going to recognize that calcium, Ca, is a type 1 metal. So we don't need parentheses. Our ionic compound means no prefixes. No prefixes, no parentheses for our name here. Okay, so we're just going to name this based on the name of the metal and the name of the polyatomic ion. So our metal is calcium, and our polyatomic ion is the phosphate ion. So the name of our compound is going to be calcium phosphate. Okay, and that was going to be choice A. Question number 50 is giving us an example of a molecular compound. Okay, we know that this is going to be molecular because we have a nonmetal and another nonmetal. Okay, and when we name molecular compounds, we are going to use prefixes. All right. And so we have 1 sulfur, we have 3 oxygens, and so our name is going to be sulfur. 3 is trioxide. Okay. Molecular compounds, you have to use your prefixes for those. All right, next question switches us over to some of the other topics in chapter 6. That naming section was took up like 10 of those review questions. So let's take a look at this next one. It says, how many valence electrons does each atom in an NH3 molecule contribute to the total valence electrons? Okay. And so when you're looking at a question like this one, think about each part of this molecule, right? If we listed this out, we would be like, we have 1 nitrogen and we have 3 hydrogens. Like that's what's in here, right? And each nitrogen has 5 valence electrons. Each hydrogen has 1 valence electron. And when we add all of those together, we're going to get a total here of 8 valence electrons. But this question asks us to look at the individual contributions. How do we know that it's 5 valence? Nitrogen is in group number 5A, and that group number tells us the number of valence electrons. Each hydrogen is going to be in group 1A. That's why we know that each hydrogen gives us one valence electron. And so here the wording is going to be like, you have to read the wording of the question kind of carefully. You're picking out your answer. Let's go back up to the slide just so we can look at what they're saying here. So we know that it's definitely going to be between choices B and C because nitrogen is contributing 5 valence electrons, which is correct. But here we have to read this part. Each hydrogen contributes 1. That's the correct answer. It's not that each hydrogen contributes 3. There's a total of 3 when all the hydrogens are considered, but each hydrogen is going to contribute 1 valence electron. Okay. All right. Based on bonding rules, which of the following is not a reasonable formula? So these bonding rules that they're talking about would be like our Lewis structures that we were making. So remember when we were talking about which elements are more likely to form diatomic molecules and which ones aren't? You can use the number of valence electrons that each one of these things have to figure out if it wants to bond to something else or not. All right, so let's look at let's look at each of these real quick. Okay, we have N2, O2, F2, and Ne2. All right, if we have 2 nitrogens, there's one of these that would hopefully stand out to you very quickly when you're looking at their individual valence electrons. When we look at the 2 oxygens, 1, 2, 3, 4, 5, 6, 4, 5, 6, right? Each nitrogen has 5 valence electrons. Each oxygen has 6 valence electrons. Each fluorine is going to have 7 valence electrons. And here they're giving us this formula Ne2. Well, neon is a noble gas, right? So that means that neon already has 8 electrons. In each of these other molecules, right? Like with nitrogen, you see how each nitrogen has 3 electrons that are singles, they're all by themselves. So for nitrogen, they'd be really happy to take all these single electrons, right? They'll line them all up in a row like this. This other nitrogen will take its 3 single electrons, line them all up in a row. And now they'll share. And now both of these are going to have 8 electrons. Oxygen will do the same thing. Each oxygen has these 2 single electrons. So instead, they'll take their 2 single electrons and they'll line them up between themselves. And they'll share. Right? 2, 4, 6, 8. Now each has 8. Fluorine has 1 single electron here and 1 single electron here. So they'll share. But neon, every electron's already paired up. So neon doesn't want to share electrons with another neon. It's already got a perfectly full valence. So that's going to be our formula that doesn't really make sense. That wouldn't happen because neon doesn't need to share any electrons. All right, let's look at the next question. Part of this one is visual, so we want to take a look at the structures that they're giving us. This one says, which of the following is the most reasonable Lewis structure for C2F2? All right, we looked at a lot of structures where we had one element that was very clearly the one that goes in the middle. In this case, we have 2 carbons and 2 fluorines, so it might not be as easy to see which one would go in the middle. As a rule, if carbon is part of your compound, put carbon in the middle. If there are 2 carbons in your compound, you can put both of those carbons in the middle and you can put the other things one on each side. Okay, carbon really likes sharing electrons and forming bonds. It's a very good middle compound, or middle element rather. The other things that you have to remember, like remember what we talked about in terms of how many valence electrons each thing has and how many bonds each thing is likely to form. Carbon, every carbon is going to come into a compound with 4 valence electrons like this. And so every carbon is going to be looking to form 4 bonds, right? Every fluorine is going to come into a compound with 7 of its own electrons. Fluorine's only going to want to form 1 bond per fluorine. So keep that in mind when you're looking at these structures. Structures that have fluorine making a double bond, no good. Fluorine doesn't want to make a double bond. Fluorine wants to make 1 bond. Okay? So choices B and C do not make any sense because fluorine does not make double bonds. Okay? Our answer choice A, F, C, C, F, this looks like what we originally sketched out. This is an okay start to a structure, but this structure is incomplete because it's not showing all of the bonds that need to form for carbon to have its full 8 electrons, right? The way that this structure is written out here, and let me stop sharing so we can get a bigger view of this. The way that this is written out here, you can imagine that around the fluorine, it still has its other valence electrons present, right? So we can imagine that's fluorine here. This is the other fluorine. Okay, but like on carbon, like carbon still has it still has these lone electrons, right? Like it's still not going to have its complete octet. And so we have to represent the structure where carbon gets to have its full octet too. And so carbon has to take these single electrons, right? And it's got to, again, it's going to move them over. So they're positioned here. They can form a bond. It's got another one, another set of single electrons up top though. All right, so when that triple bond forms, now carbon has 2, 4, 6, 8 electrons. And this carbon has 2, 4, 6, 8 electrons. Okay, this structure is the complete structure. You want to make sure that those bonds are correctly represented in your Lewis structure. In your Lewis structures, they won't always show you the electrons that are the lone pair electrons that are around your atoms, but they will always show you the correct bonds. So they won't write a single bond when they mean a triple bond. All right, so when you see carbon single bonded to another carbon, that doesn't mean the same thing as the triple bond. So you want to make sure that if you think a triple bond should be there, that's what's written there. Okay, so this is going to be the most reasonable structure for that compound. Okay, the next question asks us, which element is the most electronegative? We'll just share this real quick so you can see the options. For a question about electronegativity is a trend that you can think about like we were thinking about the size and the ionization energy. And when you're thinking about electronegativity, what you have to remember is the most electronegative atom that you're going to deal with is going to be fluorine. Okay, so remember fluorine this is your most electronegative. And down here, this is your least electronegative. And if they're asking you a question, electronegative, if they're asking you a question about which atom is, or which element is most electronegative, if fluorine is on the list, fluorine is the answer. Okay. If fluorine is not on the list, it's whatever else is around fluorine that's closest to fluorine, specifically your oxygen and your nitrogen. Those are your most electronegative, and fluorine is the most out of all of them. Okay. So fluorine is going to be the correct answer for number 54. And then our next one is, which is the least electronegative. Let's break down the trend a little bit more. I'm going to rewrite this box. Number 55. Because fluorine is not on this list, so we have to think about it a little bit differently. All right, so when you're thinking about the trend from left to right, okay, electronegativity increases when you're moving towards the right, and electronegativity decreases as you move down. Okay, that's why your smallest electronegativity is down here and your largest is up here. Also, I'm gonna have to upload new answers. If you're watching this video after I've already made the change, then don't worry about it. But the answer that's currently, that they're currently telling you is correct for number 55 is not correct on the answer key. So the answer choices that they're giving us here are going to be oxygen, sulfur, selenium, and tellurium. And if we look within the column, they're all in group 6A. Oxygen, sulfur, selenium, tellurium. Okay. And because we're working in a column, we're going to focus on this relationship, the up-down relationship. We know that the things with the higher electronegativity is going to be up top, and things with lower electronegativity are going to be towards the bottom. So here, this will be our least electronegative out of those options. Okay. Just pause that 1 second. I'm gonna fix that on my slides while we're here. Okay. Next question says, which compound forms a polar covalent bond? Okay, polar covalent bond, and they're giving us an option. They're giving us a bunch of options here. And you can answer this question without your electronegativity values, right? Because if you have electronegativity numbers, hold on, I can't talk and write at the same time. Which forms a polar covalent bond? So F, F, 2. All right. If you have the actual electronegativity values for each element here, you can subtract the electronegativity numbers, find the electronegativity difference, and then you can judge whether it's polar or non-polar that way. But there are other options in this particular question that you'd be expected to sort of rely on to be able to answer this question. First of all, when you're looking at these compounds, you should be able to pick out the non-polar ones right away in this case. any molecule that's made up of two of the same element. So in this case, we have FF and HH. These compounds are going to be nonpolar. The electronegativity of both of these fluorines is exactly the same as each other. Whatever the number is, it's exactly the same. So there's going to be no electronegativity difference. If there's no electronegativity difference, then your compound is nonpolar. So this is going to be nonpolar, and H2 is going to be nonpolar. Okay. Over here for NaF, this is a metal. This is a nonmetal. So this is not going to be a covalent bond. So it can't be a polar covalent bond. Instead, this is going to be an ionic bond. Okay. So even if you weren't sure what these numbers were, you could still be pretty sure that this is going to be your polar covalent bond, because hydrogen is less polar than fluorine, which is, or hydrogen is less negative than fluorine, which is the most negative, right? Just based on our trend line. This is going to be our polar covalent bond. All right, the next question says, which of the following molecules is nonpolar, even though it has polar bonds? All right. For 57. Which is nonpolar, even though it has polar bonds? Okay. So for each of these, sketch out your Lewis structure and get a good idea of the number of electron groups and potential lone pairs around your central atom. Okay. When you're looking to see if a molecule is polar or not, one thing that you want to look at is if that central atom has lone pairs around it. Okay. For your water molecule, you're going to have your hydrogen connected to your oxygen, connected to your hydrogen. And there are two lone pairs around the oxygen. Okay. So your OH bond is definitely a polar bond. And because you have these lone pairs here, the overall molecule is polar as well. Right? For our CO2 molecule, our carbon's going to go in the middle. We drew CO2 a few times today. We know that it's going to be carbon double bonded to each oxygen. And then our oxygens will have two lone pairs each. Now the carbon-oxygen bond is a polar bond. The oxygen's electronegative and it's pulling the electrons towards itself. Okay. But if we look at our central atom here, there are two bonding groups and there are 0 lone pairs around that carbon. And our central atom is the important one. When we have 0 lone pairs around our central atom, we're going to end up with a nonpolar molecule. This is true even if we're looking at something that has polar bonds. And that's because the oxygens will, in this case, will both be pulling the electrons towards themselves the exact same amount. So one oxygen is not going to be more negative than the other oxygen. Okay, so this is gonna end up being our correct answer, but let's just look at the structures for NH3 and H2S. Okay, for NH3, we have the hydrogen-nitrogen bond, which is polar. Our nitrogen has a lone pair. So that means our molecule is gonna be polar. Polar bond, polar molecule. Okay, so H2O, polar bond, lone pair, polar molecule. Same thing for NH3. And our final structure, H2S, is going to look really similar to the oxygen, to the H2O structure, because sulfur and oxygen are in the same group. We have two lone pairs. So we know that even if we don't know the exact electronegativity difference between hydrogen and sulfur, we know that the two lone pairs on that molecule means that we're going to have a polar molecule. Okay, so the only one of these that was a nonpolar molecule would have been CO2. All right, question number 58 asks us to find the shape of the CF4 molecule. Okay, to find the shape, first draw the Lewis structure. And then second, you're going to count your electron groups. And then you're going to do your bonding versus lone pair count. Okay. So our Lewis structure for CF4, our carbons coming in with 4 valence electrons. And our fluorines are going to be coming in with 7. All right, so we see that our bonds are going to form here. Okay. Our electron groups are going to be focused solely around our central atom. We have 1, 2, 3. We have 4 electron groups. And within those electron groups, we have 4 bonding groups. And we have 0 lone pairs. When we're talking about the shape of our molecules, remember that whenever we have 0 lone pairs, our electron geometry is going to be the exact same as our molecular geometry or shape. So in this case, with 4 electron groups, that means that our electron geometry is tetrahedral. And with 0 lone pairs, our shape is also tetrahedral. If we had more lone pairs that were scattered in, then our shape would have changed to something else. But when we have 4 electron groups, that electron geometry is always tetrahedral. All right, the next molecule they want us to find the shape of is NH3. So we'll see a slightly different end result here. All right, so we're gonna start in with drawing our Lewis structure. Okay, drew the Lewis structure. Now we're gonna count the electron groups around the nitrogen, around our central atom only. Okay, so we have 4 electron groups, which means we're going to have a tetrahedral electron geometry, just like last time, because the number of electron groups didn't change. All right, and now when we take our electron groups and we divide them between bonding and lone pairs, in this case, we have 3 bonding groups and we have 1 lone pair. Okay, and that 1 lone pair changes the shape. It's not tetrahedral shaped anymore. That 1 lone pair is going to make the shape trigonal pyramid. Okay. And our last question is a pretty easy question on intermolecular forces. This question just says, which type of attraction is found between nonpolar molecules? Nonpolar molecules, there's only one option for intermolecular forces. It's going to be the weakest of the intermolecular forces, and that's going to be dispersion forces. Dispersion forces are the only type of intermolecular force that something that is nonpolar can have. Okay. And that's it for your review questions. So hopefully that helps out in your studying, and then we can go over any other questions that you have in class before the exam.